So let's now continue with the proof of part 1 of additivity. So just a reminder firstly, here is the interval AC, and we have divided it by the point B here into the interval AB and the interval BC. And we are saying that the function is Riemann integrable over the interval AB and it's Riemann integrable over the interval BC. And this is how we're denoting the values of those integrals. So that's the integral over the interval AB. And then here is how we're denoting, of course, the value of the integral over the interval BC. What we now want to show is that it is Riemann integrable over the entire interval AC, and that the value of its integral is the sum of these two things. And we're going to use, to do this, the strategy that we looked at in general in the previous part. So we're going to have some x value, and we're going to show that the upper Riemann sums get indefinitely close to it from above, and that the lower Riemann sums get indefinitely close to it from below. So what x value do we need to use? Well, we need to use whatever the actual value of the integral is going to be over the interval AC. Now, we know what we're trying to prove. We know the additivity property is going to overall be true. So what guess are we going to take for x? Well, of course, we're going to take the sum of these two things. So we're going to take as our x value the integral of f over the interval AB plus the integral of f over the interval BC. So this is going to be our x value, and now what we need to do is show that there are upper Riemann sums over the interval AC that get indefinitely close to this value from above, and that there are lower Riemann sums over this interval AC for the function that get indefinitely close to this value from below. So let's begin by showing that there are upper Riemann sums that get indefinitely close to x from above. Now, how are we going to do that? Well, remember what we said in the previous part. Formally, how we show that something gets indefinitely close from above, we need to show that for all epsilon greater than 0, you can find an upper Riemann sum that is within that interval from x to x plus epsilon. And if you can do that for all epsilon, then you can do it even for the indefinitely small ones, and therefore that captures formally this concept that there are upper Riemann sums getting indefinitely close to this value x. So let's draw this on the picture. Here's the real line, here is x, and now let's say here is x plus epsilon, and we're going to let epsilon be some general positive real number, and since we're putting no other conditions on epsilon, if we can show that for this general epsilon that we can find an upper Riemann sum that is inside this interval, then it will hold true for all epsilon greater than 0, and hence we'll have shown for all epsilon greater than 0 that this is true, and therefore we'll have got this fact that there are upper Riemann sums getting indefinitely close to x. So we need to find an upper Riemann sum then that is inside this interval from x to x plus epsilon. Now it's going to be an interval that is closed at the lower bound and open at the upper bound. So it's the interval from x and including x to x plus epsilon and not including x plus epsilon. Now, why is that? So the reason we don't include x plus epsilon is just convention. In analysis, we always talk about distances being strictly less than epsilon, not less than or equal to epsilon. Now, you could have written all of analysis with less than or equal to epsilon instead. However, convention is convention, so we'll stick with convention. So we're not including the point x plus epsilon here. Why are we including the point x? Because if we manage to get an upper Riemann sum that is bang on x, then that's distance 0, so that's fantastic. You know, we're trying to show that there are upper Riemann sums getting indefinitely close to x. If we've got one that is distance 0 from x, then that's fantastic. So we should include x here. Now, in general, of course, we won't be able to find an upper Riemann sum that is actually equal to the value of the integral. Only for very simple functions will that be the case, that there are upper Riemann sums that are equal to the actual value of the integral. But so that our arguments include those simple ones where you might have upper Riemann sums, such as the constant functions, for instance, where all of the upper Riemann sums over whatever dissection are equal to the value of the actual integral, we should include x here in our interval. So my aim is to then show that for any epsilon greater than 0, that there is an upper Riemann sum inside this interval x to x plus epsilon. Now, how am I going to do this? Why, I'm going to use the fact that the function is Riemann integrable over the interval ab, and that it's Riemann integrable over the interval bc, and that these are those values for the integrals. Now, to make our life easier, I don't want to have to continually write out these integrals, so I'm going to give them easier names, just like the fact that I didn't want to have to continually write this out, so I gave it an easier name x. I don't want to have to write these out either, so I'm going to give them easier names too. I'm going to call this one x1, and I'm going to call this one x2. So that means that x, written in our new notation, is going to be x1 plus x2. So before we go any further, let me just outline my strategy here. So to find an upper Riemann sum for the function over the entire interval AC that is inside this interval, what I'm going to do is find upper Riemann sums just over the subintervals, so find an upper Riemann sum over the subinterval AB that is within epsilon over 2 distance above the value of x1 here, and then I'm going to find an upper Riemann sum just over the interval BC that is within epsilon over 2 distance above x2 here, and then both of those will have dissections for the subintervals. What we will do is we'll just combine those dissections together to make a dissection for the overall interval AC, and we'll then be able to show that the upper Riemann sum for the function over the entire interval AC with that combined dissection is inside this interval from x to x plus epsilon. So let's start off with the interval AB. So on the real line, here is the value of x1, and now consider the interval from x1 to x1 plus epsilon over 2. So I'm going to this value plus epsilon over 2 but not including it. Now I claim that there is always going to be an upper Riemann sum over this interval AB that is inside that interval. Whatever epsilon is, as long as it's greater than 0, you can divide it by 2 and then look at this interval from x1 to x1 plus epsilon over 2. I guarantee you will be able to find an upper Riemann sum that is inside here. Now why is that? Well, firstly, it's going to definitely be greater than or equal to this value, x1, because all of the upper Riemann sums are greater than or equal to that value, because it is the infimum of the upper Riemann sums, remember, for this interval AB. Now, why can I find one that's strictly less than x1 plus epsilon over 2? Well, if I couldn't do that, that would mean that this was a lower bound for the upper Riemann sums, which would contradict this being the greatest lower bound, being the infimum. So that means that there must be an upper Riemann sum that is strictly less than this value, x1 plus epsilon over 2. So we'll put that here. So we will call this the upper Riemann sum over d1 of f. So d1 is a dissection of the interval AB. Remember, it's not a dissection of the entire interval AC, it's just a dissection of this interval, so it's cutting this interval up. So this must exist. I must be able to find such an upper Riemann sum. Now, the exact same argument holds true for the interval BC. So, drawing another picture here, here is the value of that integral of the function over the interval BC, and again, we can imagine looking at this interval from x2 to x2 plus epsilon over 2, and again, there is guaranteed to be an upper Riemann sum over this interval BC that is inside there. Again, it's guaranteed to be greater than or equal to the value of the integral because that's the infimum of all the upper Riemann sums. And the reason there's guaranteed to be one that's strictly less than x2 plus epsilon over 2 is again because if there were no upper Riemann sums in here, then that would mean they would all have to be greater than this, greater than or equal to this, and therefore this would qualify as a lower bound for the upper Riemann sums, which would contradict this being the greatest lower bound, being the infimum. This one would be a better candidate for the infimum than this one. And that's why there is guaranteed to be some upper Riemann sum that's inside that interval. and we'll call this one the upper Riemann sum over some dissection which we'll call D2, which remember is now a dissection just of the interval BC, so it's chopping up this interval into bits. So we've got D1 that chops up the interval AC, D2 that chops up the interval BC. Of course, we're going to create a dissection of the overall interval AC by just combining these two together. We'll do that in just a moment. So, just to write down what we've got now, so we know that this upper Riemann sum over D1 of F is inside that interval from x1 to x1 plus epsilon over 2, not including x1 plus epsilon over 2. And we know that the upper Riemann sum over D2 of F is inside the interval from x2 to x2 plus epsilon over 2, again not including that value. Now what we are of course going to do is combine those two dissections together to get an overall dissection of the interval AC. So just to show this explicitly on a picture, here we have AC, here is B in the middle here. Now the dissection D1 is a dissection of the interval AB, so it's cutting this interval up, and just for simplicity we'll just have it cutting it up into, let's say, 4 pieces then. So overall it's a sequence of 5 numbers therefore, starting with A, then this one, then this one, then this one, and then ending with B here. And then we have D2, which we'll show in blue, and I might just go over D1 here, it's in red. And D2, and for simplicity let's just have it dividing it up into 3 pieces here. So it would then be a sequence of 4 numbers, starting with B, then this one, then this one, then ending with C. So the dissections D1 and D2 share only one common number. The last number of D1 is the same as the first number of D2. So what we can now overall do is use these two dissections to create a dissection of the overall interval, and you can see that it's partitioning the interval up into 7 subintervals, this bit, this bit, this bit, this bit, this bit, this bit, and this bit. And overall it consists of 1, 2, 3, 4, 5, 6, 7, 8 numbers, a sequence of 8 numbers. So it's the number in here plus the number in here minus 1, because we're counting B twice if we were to just add the number of numbers in each of them, because they both share B. So we'll call that overall dissection that you create of the interval AC, we'll call that the interval, the dissection rather, D bar. Now let's consider creating the upper Riemann sum of D bar, of F rather, over this dissection D bar. Now, I claim that this is actually just going to be the sum of the upper Riemann sum of F over D1 plus the upper Riemann sum of F over D2. Now, why is that going to be the case? Well, remember how the upper Riemann sum is defined. You take the length of each of the subintervals and you times it by the supremum of the value of the function over that interval. And you do that for every single one of these intervals. Now, when you're constructing this one, you'll take the length of this, times it by the supremum over that interval, add it to the length of this one times the supremum over that interval, add it to the length of this one times the supremum over that interval, add it to the length of this one times the supremum over that interval. Now, when you're doing it in the overall bigger dissection D bar, you'll be doing the exact same thing. You'll be taking the length of this one times it by the supremum. The supremum of the function won't have suddenly changed because you've extended your range of interest. You know, you've extended the interval a bit, you've added on this bit BC, but it won't change this first part of the calculation. So the first part of calculating this upper Riemann sum over our bigger dissection D bar of the entire interval is still going to be exactly the same as what you would have done when you were just considering doing it over this interval AB, which is what's going to happen here. So actually this first part of the calculation is exactly the same as this bit, and then of course the second part of the calculation where you're multiplying this, the length of this subinterval times the supremum of the function over there, then take the length of this one times its supremum, take the length of this one times its supremum. That's going to be exactly the same as you would have done here. So yes, this is a bigger calculation because you need to do both this bit and this bit, but the actual thing that you do in this calculation hasn't changed. So it's just do this calculation, and then add them together. So I hope you understand why that is going to be the case. Now my next claim is that this upper Riemann sum over this combined dissection d bar is going to be in my desired interval from x to x plus epsilon. Now why is that the case? Well, it's because I know something about where these two values lie. This one lies inside this interval, and this one lies inside this interval. So when I add them together, I can say something about what this value is going to be. So let's think about what the smallest value this can take on is. Well, the smallest value this can be is x1. The smallest value this can be is x2. So that means the smallest value that the sum can be is x1 plus x2. Now there is a name for x1 plus x2. That's just the sum of the two integrals. Remember, here's the definition of x1, here's the definition of x2, and that is of course what we called x. So the smallest value that this sum can be is the value x. Now, we also know that this value is strictly less than x1 plus epsilon over 2, and that this value is strictly less than x2 plus epsilon over 2. Therefore, when we add them together, the value is going to be strictly less than x1 plus x2 plus epsilon over 2 times 2, which is epsilon. So it's going to be strictly less, therefore, than x, which is x1 plus x2, plus epsilon. So it's going to be inside this interval from x to x plus epsilon because of the intervals that these two things are contained within. So what I've overall succeeded in doing here is I have shown that for a general epsilon greater than 0, it is possible to find an upper Riemann sum that is inside this interval from x to x plus epsilon. How did I do this? Well, I went to the two individual subintervals and I found upper Riemann sums over those subintervals that were within epsilon over 2 distance above their individual integrals, so the x1 and the x2 values. And then we saw how if we combine their two dissections together to make an overall dissection of the overall interval, that the upper Riemann sum using that combined dissection over the overall interval is just the sum of those two individual upper Riemann sums over the subintervals. And then because of the restrictions that were placed on these upper Riemann sums, I'm then able to conclude that my overall upper Riemann sum is inside the desired interval. So I have succeeded then in showing that I can find upper Riemann sums that get indefinitely close to this value x from above. We'll have a break here, and in the next video we'll do the corresponding proof for lower Riemann sums getting indefinitely close to x from below, and it's the exact same idea, just the mirror image of it.